Audio Jungle. Audio Jungle.
All right, so now we have impulse to weight ratio of rocket system. So these are the small topics, okay? I mean one-liner things, but we need to know that. So it is defined as total impulse to initial vehicle weight. Okay, so if I say initial vehicle weight, that means that rocket is what now going to lift off. So that propellant of the rocket, you can say it is going to start burning now. It is not yet started, yes or no? So in that case you have to take this is the exit. We have a propellant here, this is the propellant, you can see, okay, here. All right, now so three things we have, okay. This is the, here suppose this is the payload, so mass of payload, mass of payload will be denoted by ml. This is what mass of propellant, it will be denoted by mp, okay. And you can say that structural mass of the vehicle, it will be denoted by ms, okay. So what is the total initial weight then? Total initial weight of rocket, it will be denoted by m naught, okay. So what is the m naught? M naught is nothing but, you check, it is first start from the top, it is ml, which is the mass of the payload, okay. Then mass of the propellant mp plus mass of the structure, okay. Need to remember this because now we are moving towards numerical part, so This all points what I'm going to mark here, it is very important and it is the foundation of the numerical. Once you understood basic thing, then definitely you will able to understand numerical part very easy. Okay, in very easy way you will understand, otherwise there will be lots of confusion in the rocket problems. So initial to weight ratio of rocket system, yes, sorry, impulse to weight ratio of rocket system. So what is the impulse to weight ratio? Impulse to weight ratio is nothing but I by W. Okay, and it is I is nothing but that is the uh, uh, total impulse. So I must say it is IT, total impulse divided by total weight, and this weight is nothing but initial vehicle weight. So what is the initial vehicle weight? I can write W naught. So IT we know it is nothing but ISP into G. Okay, sorry, it is not ISP into G, it is, let me write this, ISP into mass of the propellant. Check it, total impulse, I am saying. So see, ISP into mass of propellant divided by W naught is nothing but mass of the payload plus mass of the propellant plus mass of the structure. Okay, and it is G. All right, so this formula is what very important. This is called impulse to weight ratio. Okay, so I'll put in box. So sometimes they will give to you impulse to weight ratio. So you should know what is the mean of initial weight. Initial weight means that burning is what just started. It is not completed. If burning is what completed, then MP will be, mass of the propellant will be 0, because propellant is what burning is what completed, then mass of the propellant will be 0. But here I am saying initial weight of the rocket system, it means that mass of the propellant is still there, it is not completely burnt, it is just going to start burning process and all. Okay, number 1, this is the point 1. All the articles what I am writing here, it is based on numerical. Okay, numerical they are asking based on this parameters what I am writing here. So second parameters we have, it is called mass ratio. So these are the terminology they are using in the numerical part. Okay, that directly they will say, okay, mass ratio is this. If they said mass ratio, then what you will understand? For that reason, it is required to go with this theory part. Okay, one-liner theory we have, mass ratio. Okay, mass ratio, MR. What is the mass ratio? So mass ratio is nothing but, the mass ratio is defined as the final mass. Okay, it is the ratio of, in short I am writing, okay, it is the ratio of final mass. If I say final mass after rocket operation, if I say it is the ratio of final mass after rocket operation, so what is the mean of it? After rocket operation, so definitely if I say after rocket operation, it means whatever the amount of the propellants, it is completely consumed, or it is completely burned, you can say, or it is consumed. So in bracket also required to write, or after propellant were consumed, bracket, yeah, to the initial mass, to the initial mass m naught, to the initial mass before rocket operation, before. Okay, so this term you need to remember. So what is the MR? MR is the mass ratio, and it is denoted by m small f divided by m naught. What is the mf? Mf is the final mass after rocket operation divided by initial mass before rocket operation. So this ratio is very useful, you need to remember. Okay, this ratio is very useful. Whatever the ratio I am writing here, you please remember. Okay, because I will use each and every ratios here in further points. Okay, so this is the second points. What is the third points? So it is nothing but propellant mass fraction. Propellant mass fraction, it is denoted by xi, or in somewhere it is called as zeta, xi or zeta, whatever you want to take, you can take for the notation. Okay, it is denoted by, here I am just writing zeta I have written. So what is the propellant mass fraction? So it is defined as the ratio of propellant mass MP to the initial mass. What is the initial mass? M naught. In bracket I can write, and propellant mass is what? MP. Okay. So what is the zeta? Zeta is nothing but mass of the propellant divided by mass of initial mass of the system. What is the mass of the propellant? Here you check, you can check. So mass of the propellant, if you check what is the mass of the propellant, so mass of the propellant MP will be what? M naught minus in bracket ML and MS. Yes or no? Or in other word, what you can say, it is MF. MF is what? MF is the final mass after rocket operation. So even though after rocket operation we will have a mass of the payload and mass of the structure, yes or no? We are considering that payload is what? Not launched. You just say it is only, we are talking about the, otherwise you may think like, okay, after rocket operation means what? Whatever the payload we are having, like satellite or anything, we have launched. No, I mean we have pushed it into orbits and all. No, don't think in that way. You just think like, okay, if rocket operation before mass of the rocket before operation and after operation, so it is related to the mass of propellant. If I say before rocket operation, it means mass of propellant is what? Is still there, it is not completely consumed. If I say after mass of the system after operation, so it means after operation, it means that mass of the propellant is what? Completely consumed. That's the mean of it. Okay, so MP will be 0 that time. Now, so here if you want to write the mass of the propellant, so mass of the propellant, you can say what is the initial mass? M naught minus final. Okay, minus final divided by initial mass M naught. Okay, and this is also, you can say, if you go for this M naught minus MF, what is the initial mass? M naught. So initial mass M naught, you can say mass of the propellant, because you are talking initial, so M naught will be the mass of the propellant, because initially propellant will be there, plus MF plus MF. Okay, so, and in, or you can say M naught is nothing but, if you want to write complete, you can write M naught minus MF. What is the initial mass? Initial mass is nothing but mass of propellant plus mass of the payload plus mass of the structure. The full length also you can write, otherwise MP plus MF you can write. Yes or no? Because if you see what is the m naught initial mass, or what is the, if I say what is the minus, what is the final mass, so you can say final mass is nothing but initial mass minus mass of the propellant, because this mass of propellant will be that part will be deducted. Why it is deducted? Because you are talking about final mass, and final mass means what is the mass of the rocket system after operation. So after operation, this mass of the propellant will be removed, because it is now completely consumed. So you need to remember this final mass is nothing but always initial mass minus mass of the propellant. So somewhere if it is written m naught, so what is the mean of m naught? M naught is nothing but mf plus mp. So this part here I have written this. Or this initial mass also you know very well, it is nothing but mass of the payload plus mass of the propellant plus mass of the structure. This is also, because m naught here itself you have seen first, this m naught. What is the m naught? Ml plus mp plus ms. So the same thing I have written here also. Okay, so this thing is need to careful, otherwise so much confusion while you are solving numericals, so much confusion you may get. So each and every lines you need to understand. Okay, now so another format also you can have, because this is numerical point of view very important, this mass fraction, propellant mass fraction. So what I told you, mass propellant mass fraction is nothing but mass of the propellant mp divided by mass of the initial mass of the system. So initial mass you can write m naught, yes or no? And you have seen this mp is nothing but, what is the mp? Mp is nothing but m naught minus mf. So it is m naught minus mf divided by m naught. You have written this is here, this part. Okay, now here only you can break again. So again one more formula you will get. You will have m naught by m naught separately you have taken this, and if we check, it is nothing but 1 minus mf by m naught. So zeta is nothing but 1 minus final mass by initial mass. Check what is the final mass by initial mass. Mf by m naught is nothing but mr, which is called mass ratio. So this is 1 minus mr. This is very important. Okay, this is very important result, and it is very useful for the numerical, and numerical based on this they are 100% they are asking for one day exam. If you go separate even exam for ISRO or HL, then you may get numerical based on these formulas. I mean, whatever I'm explaining, it is very important, okay, for all exams. So zeta is nothing but 1 minus mr, where zeta is nothing but propellant mass fraction, and mr is the mass ratio. Okay, so now you can get here like mr is always less than 1, yes or no? Mr is always less than 1. Mr is less than 1. Why it is? Because m naught is always greater than mf. What is the m naught? It is before operation. So if before operation, definitely mass will be more, because propellant mass is still there, but mf is after burning. So it is very important. Okay, mr is always less than 1, because you can draw the plot also. Plot is not required, but you can draw if you want. So this is the propellant mass fraction, and it is always greater than 1. Okay, always greater than 1. Greater than 1 in the sense, not greater than 1, you can say it is positive value, or you just remove this part. But that based on consumption of mr, you can draw a zeta also. You are not going to draw plot, so it is not required. Just I was saying, like, if you want to draw the plot, then zeta based on mr variation, because 1 is constant, so once mr is what changing, then zeta will be changing, so you can draw the plot also. So for one day exam, definitely graph based question will not come, but in semester and all, you might have solved in your during your BTech course, based on the plot you had solved the numerical. So here it is not required actually that. Anyway, now this is what propellant mass fraction. Now we'll go for the next, which is nothing but this is the one problem we need to solve here, and then we'll go for the next topic. So we have problem based on this performance parameter. So this is what problem number 1. Okay. Now a rocket engine with chamber pressure of 4.5 megapascal and nozzle throat diameter of 110 mm produces thrust of 17 kilonewton by consuming propellant flowrate of 7.5 kg per second with calorific value of 25 megajoule per kg if the flight velocity happens to if the flight happens to be 850 meter per second 850 meter per second determine number 1 specific impulse, number 2 effective exhaust velocity, number 3 specific propellant consumption, and point 4 is thrust power, point 5 is thrust coefficient, and you know it is denoted by ISP, effective exhaust velocity, SPC, thrust power, TP, and CF. Thrust power also you can say FP if you want, it's your choice. Check here. So 4.5 megapascal, this is what given. Chamber pressure is what 4.5 megapascal. Throat diameter you can say DTH, how much 110 mm, 110 mm produces that thrust they have given to us, it is 17 kilonewton, and mass of the propellant m dot p is given, sorry, 7.5, not 17, it's a 7.5. 7.5 kg per second. Okay, calorific value means here they have given a CV they have given to us. CV, that is the calorific value, which is nothing but 25 megajoule kg, and last is the flight velocity they have given to us. It is how much? At 50 meter per second. Okay, so now solution for this problem is simple one. Number one, what is the number one? It is specific impulse. What is the formula for this? It is ISP. What is the ISP? It is thrust F divided by m dot p into g. What is the thrust? It is given 17 kilonewtons, so 17 into 10 power 3. M dot p, mass flow rate of the propellant, it is given 7.5. G they have not given, but you can consider 9.81. Okay, if you solve this, then approximate you will get, as you have calculated, 231.06 second. So this is the ISP. This is number one. All right, now we'll go for the number two. What is the number two? Number two is nothing but effective exhaust velocity. Okay, so what is the effective exhaust velocity? As you know, it is nothing but ISP by G. You check that formula ISP, that one box I had given, and in the box many formulas was there. So there I had given ISP is equal to V equivalent or effective velocity into G. ISP is equal to V effective into G. So what is V effective? It is ISP by G. What is the ISP? Just now you have calculated 231.06 divided by G is nothing but 9.8. Now if you what formula I had taken? Wait, this value V effective is so much. This formula is what? ISPG is equal to V effective by G. If you remember, no, I made mistake. Sorry. Now correct this. So actually, I think little bit hurry. I don't know why. ISPG. If you remember, we had proved that it is V effective into G. All right. So what is the V effective by G? Now it is correct. It was V effective. It was proved V effective by G, if you remember. So what is V effective now? V effective is nothing but ISP into G. So what is the ISP? You have calculated 231.06, what I remember, into 9.8. If you do this calculation, so here approximate you will get 2266.7 meter per second. This is the value. Please check the value of this formula. If you remember, we had proved ISP is equal to we had proved this. It was f dot f is f divided by m dot pg. If you check f divided by m dot p into z, what is the f? F is nothing but v equivalent or effective into m dot p divided by uh, m dot p into g. M dot p cancel out. So what you will have? You will have isp is equal to v effective by g. So you use that formula. Okay. So it is very tough for me to remember the formula, but anyway. Alright, so this second value you have calculated. Now we'll go for the third value. What is the third value? Third value we have a specific propellant consumption. It is nothing but SPC. Okay. What is the SPC? SPC is nothing but I had given one formula and it was very large in box. Many formulas I had given for SPC, but finally if you remember it was 1 upon ISP. What is the ISP here? It is given 231 I think. 231.06. If you solve this, what you will get? You will get 0.0043 kg per Newton second. This is number 3. Okay. We'll go for number 4. What is the number 4? Thrust power. Thrust power. Okay. What is the thrust power? It is FP. What is the formula? Thrust power is nothing but power is what? Force into area. What is the force? Force into velocity. What is the force? Thrust. Force into velocity. What is the thrust you have here? 17 kilonewton. So 17 into 10 power 3. And velocity of the vehicle they have given to us how much? It is here it is given at 50 meter per second. At 50. If you solve this, then approximately you will get 14.4 because it is power, so it is watt. So what is the thrust power? It is nothing but 14.45 megawatt. This is number 4. Now we'll go for number 5. So what is the number 5? Number 5 is thrust coefficient. What is the thrust coefficient? It is CF. By formula we know CF is nothing but thrust force divided by PC into ATH, throat area. What is the thrust force? It is I think 17 kilonewton they have given to us. Check 17 into 10 power 3 divided by PC. If I am not wrong, it was 4.5 mega bar. Check it. 4.5 megapascal. Sorry, megapascal they have given. And diameter mm it is given 110. So 110 mm they have given diameter. Now so we'll write 4.5 megapascal, so 10 power 6 into area is nothing but 5 by 4 into diameter 110. So 110 mm you convert it into meter, so it is 0.11 5 by 4 d square. If you solve this 0.3975. One more you can add here in problem itself. 6 number. 6 is very interesting actually. It is C star. Okay, we need to find C star. 6 number. What is the 6? Characteristics velocity. C star we need to calculate. Add that. So 6 number is nothing but characteristics velocity. What is this? It is C star. Check as per given data what we have find yet. So what is the C star? Many formulas I told you yesterday. I had given all the parameters. These parameters, 6 parameters you have calculated, and all 6 parameters I had explained in my last lecture. So if you check there, C star in different format it was given in different term. So one it was V effective divided by CF. If you check this formula is available or not, this one you can use because V effective you have and CF you have. What is the V effective? V effective you have 2266.7. So it is 2266.7 divided by it is nothing but 0.3975. If you solve this, then you will get how much? So it is 5698 meters per second. Done. So if you go for the efficiencies, so we have a two efficiencies, okay, and it is nothing but thermal efficiency and propulsion efficiency. It is denoted by eta P and it is denoted by eta TH. So in similar way what you had seen for the jet propulsion, same way we can write efficiency formula for the rocket propulsion. So here I am just going to write directly this formula, eta TH. It is nothing but V equivalent square plus V square divided by 2 combustion chamber efficiency into heat value. Okay. One more thing I just want to add here. This thermal efficiency is basically in word. It is nothing but formula I will write: engine power output. Okay. Engine power output divided by available chemical power developed by combustion. So in word also now you have formula how it comes, how this formula comes. This engine power output is nothing but 1 by 2 m dot P V equivalent square plus V square divided by that available chemical power. It is nothing but eta Cc into m dot P. All formulas you are now aware with this, like what is the eta Cc m dot phv. You know in combustion chamber you had seen that available chemical energy. I had written many times that available chemical energy in combustion chamber. So eta Cc in jet propulsion it was m dot f into hp, but it is rocket propulsion, so m dot p for mass flow rate of the propellant. Rest everything is what same. So it is V equivalent square plus V square divided by 2 times eta Cc m dot P into H. Alright. So this formula you need to remember. So how it comes, that also I have in 2 lines explained. So at least this will be clear in your mind. Okay. Sometimes source is required to know actually. Okay, so what is the source? That source you should know. In between steps you can remove, no problem, but at least source you should know. So what is the source? This is the source. All right, fine. This is what thermal efficiency. In the same way, we can go for the propulsive efficiency. So point 2, propulsive efficiency. So just like in jet propulsion we had seen propulsive efficiency, we have propulsive efficiency for the rocket propulsion also, rocket system. So first I will write in word. So eta P is nothing but it is propulsion power or thrust power based. I will write thrust power. Thrust power divided by engine output power. Engine output power. Thrust power divided by engine output power. So if you solve this, so final formula I'm just going to write. Okay, after getting all the manipulation, 2-3 steps you have. So this formula will be 2 into V divided by V equivalent divided by 1 plus V upon V equivalent square. See, in similar way you had seen for the jet propulsion also, there was some different thing, but similar way we had seen in jet propulsion also. So it is eta P. In jet propulsion this square was not there, rest everything is what same. So it is nothing but 2 into sigma divided by 1 plus sigma square. In jet propulsion it was 2 alpha divided by 1 plus alpha. What is the sigma? It is nothing but speed ratio. This is called propulsive efficiency. This is called propulsive. What is the sigma then? Sigma is nothing but V upon V equivalent. It is called speed ratio. That's all. Done. Okay, you need to remember. So this is the propulsive efficiency. Alright. Overall efficiency, obviously thermal efficiency into propulsive efficiency will give the overall efficiency. Done. So all right, so now this is the problem number 2, and this type of question they are asking in exam. Okay, one question will be like this and another question will be related to multi-staging. 2-3 questions they are asking every year, okay, in GATE Aerospace. So problem number 2. All right. So it's a simple one. A rocket having an effective jet velocity of 1100 meter per second and flying at 8500 kmph kilometer per hour has propellant flow rate flow rate of 6 kg per second if the heat or if the calorific value of propellant is 43 megajoule, find number 1 eta P propulsion efficiency, eta TS thermal efficiency, eta E overall efficiency. So efficiencies are the part of your GATE syllabus or not, but rocket propulsion is the subject, so each and every topics they will not mention in syllabus, so you need to consider, okay, efficiency they can ask to your exam, in your exam, okay. You cannot say like, okay, efficiency that is not in your syllabus, because as I told you, it is the part of that rocket calculation, okay. So you need to find this. So now what are the given data here? Need to check. Given, what they have given, they have given V effective or V equivalent is nothing but 1100 meter per second, and the vehicle velocity is nothing but 8500 kmph. If you convert it into meter per second, so you will get 236.11 meter per second. Okay, mass of the propellant here, it is given how much? 6 kg per second, and heat value for the propellant they have given, it is 43 megajoule per kg. Now for this problem directly we can calculate first eta P. So I have directly given the formula for eta P. So what is the formula? It is 2 sigma divided by 1 plus sigma square, 2 into, what is the formula of it? That formula I have given here, see, it is V upon V equivalent or effective, right? So V upon V equivalent divided by 1 plus V upon V equivalent. So everything you have here, 2 into, what is the V? V is nothing but 236 divided by 1100, 1 plus divided by 1100. Find it. 76.66 percentage, because by default propulsion efficiency is what in percentage, so I am writing it into that. This is the first one. Second one is what? It's a thermal efficiency. So what is the thermal efficiency? 0.2. You have written the formula thermal efficiency. It is V effective square plus V square divided by 2 eta Cc m dot P HV. So I will write here V equivalent square plus vehicle square 2 into eta Cc chamber combustion chamber efficiency HV into mass of the propellant. So if you check here, V effective equivalent, it is given I think 1100 plus flight vehicle speed is 236.11 divided by 2. Combustion chamber efficiency they have not given, so you consider 100%, so it is 1. Heat value I think it is 43 megajoule, no? Megajoule. So 43 and for 6 into mass of the propellant, I think it is 6 kg per second. So if you calculate this thermal efficiency, so Yes, this one is approximate 7.89%. Fine. What is the third one? Eta O. So as I explained in jet propulsion also, eta O is nothing but thermal efficiency into propulsion efficiency. Propulsive efficiency. What is the thermal efficiency? 7.89. So you can write 0.00 not 0.07879 into what is the propulsion efficiency? It is 0.766, no? 0.766. If you do this overall efficiency approximate, you will get, then calculate this value, how much it is. 0.0789 into 0.766, so it is 0 0.06043, but in percentage it is nothing but multiply by 100, so you will get 6 point something. This is the propulsion efficiency. Overall efficiency. Alright, this is the overall efficiency. Nice. Done. So rocket engine, this is problem number 1. Okay, now check this problem here. A spacecraft dry mass, see a new word came here, so I will explain. So once you are solving numerical, so new terminology if you get, then you need to understand, okay, because different terminology they are using in the problems. So dry mass is 75,000 kg. 75,000 kg, and the effective exhaust gas velocity of its main engine is 3,100 meter per second. How much propellant must be carried if the propulsion system is to produce 1 produce a total delta V of 700 meter per second. All right. Now, to check, they have given spacecraft dry mass. So dry mass, it is also called burnout mass or final mass. I explained already what is the final mass. So final mass they have given 75,000. So in one previous numerical, I think there I had calculated velocity 231 something. That was a mistake, calculation mistake. Okay, so please, once you are calculating any value, please cross check and then you need to tell to me that value. Okay, anyway, 75,000 kg. Okay, and effective exhaust velocity, it is given how much? 3,100 meter per second, and delta V here it is given now. They are saying calculate how much propellant must be carried. So they are asking the amount of the propellant. Okay, so we need to find propellant mass, not mass flow rate, propellant mass. So what formula we have? Change in velocity formula. We have a change in velocity formula, which is nothing but delta V. It is V equivalent ln 1 upon mr. If you check, I also can write this formula as a ISPG ln 1 upon mr. But in the problem, V effective exhaust velocity equivalent velocity they have given, so I will use this formula ln 1 by mr. And mr you know very well. What is the formula for mr? It is mf divided by m naught, or you can say V equivalent ln m naught by mf. If you check, this is what delta V. What is the m naught by mf? M naught by mf is nothing but E del V by V equivalent. Okay, or you can say m naught is equal to mf e to power delta V by V equivalent. So this this was the derivation, and already I had derived. Okay, I had derived, but again here I have given because I don't remember the formula exactly. So m naught you have now. What is m naught? mf e to power delta V divided by V equivalent. Everything they have given. mf, what they have given? Check mf. It is 75,000. No, it is 75,000. So keep all values here. E to power delta V they have given 700 divided by V effective exhaust velocity they have given 3,100. Calculate this value. If you calculate, so this value approximate to 94,000 kg. This is the initial mass. This is the initial mass. Okay. Initial mass of rocket system. So what will be the mass of propellant? Mass of the propellant It is MP, and what is the MP? I told you in previous lecture, m naught minus mf. Initial minus the final mass. So you will get the amount of the propellant. What is the initial mass? It is 94,000 minus what is the final mass? It is dry mass actually 75,000. If you do this, you will get I think 19,000. Yeah. So this mass of the propellant. So this is very easy question, and this type of question they will ask formula based problem, and that problem they will ask such that you can solve in 2-3 minutes, no? Not very lengthy question they will ask to you. But here for practice we have to solve a big question, but in examination if you see all data will be given to you, and if you know the formula within 2-3 minutes you can calculate. So now we'll go for the next problem. Problem number 2. So this is nothing but, this is quite good question. A rocket vehicle has the following data. Okay, so need to check this. They have given initial mass. So our notation for initial mass is m naught. How much it is given? 300 kg. It's a very small rocket. Initial mass. Then they have given final mass. What is the final mass? It is 180 kg. Then they have given payload mass. In our notation, what is the payload mass? ml. How much it is given? 130 kg. Burn duration. It is also called burning time, and it was denoted by TB if you remember. Burn duration they have given 5 seconds. And then specific impulse. It is denoted by ISP, and how much it is? It is 280 seconds. Okay, we need to find determine number 1, determine the mass ratio. Means MR we need to calculate, number 1. Number 2, propellant mass fraction. Propellant mass fraction, it is PF, and it was also I think zeta, what I remember. Point 3, propellant flow rate. Okay. Number 4, propellant flow rate, then thrust to weight ratio. Thrust to weight ratio. And impulse to weight ratio. total impulse divided by weight. These are the data you have to calculate, need to find. Now we'll go for the solution. So as per given data, you check here. Now for this rocket, we can say this is ml, mass of the payload. This is the mass of the propellant. Okay, the initial mass is what, m naught. All right, so now check the solution for this problem. First we need to calculate mass ratio. So mass ratio is nothing but, as already I had mf by m naught. Okay, not m dot f, it is mf by m naught, or mb by m naught, which is nothing but naught. So final mass they have given to us 180 divided by 300. Okay, so this is nothing but 0.6. So MR is 0.6. This is the first answer. Then second, what is the second we need to calculate here? Second is nothing but propellant mass fraction. It is called PF or zeta. So what is zeta? It is nothing but mass of propellant divided by initial mass. What is the mass of propellant? I had given this expression, m naught minus mf divided by m naught. Initial mass they have given to us is 300 minus final they have given us 180 divided by 300. If you solve this, you will get 0.4. Please keep calculating correctly. You will get data. Now the third point is propellant flow rate. So propellant flow rate means m dot p. What is m dot p? It is mp, mass of propellant divided by burning time. So if you check m dot p, what is the mass of the propellant you had calculated? It is 300 minus 180. So I think 120, right? So 120 divided by mp is 120 and burning time is, if you check, it is 5. So how much you will get? It is 24 kg per second. This is what? Propellant flow rate. What is mp? mp is simple, 300 minus 180 divided by burning time. And what is the burning time? If you check burning time in the problem, it is given 5 seconds. it is given 5 seconds. All right. Now moving ahead for the next point, and this point is nothing but fourth point, I think. So what is the fourth point? Thrust to weight ratio. Thrust to weight ratio, thrust to weight ratio, or F by W. So how to get thrust? Simple. If you remember, the thrust is many formulas I had given, and in that formulas I had given, that was F is equal to, which is the thrust, and it was ISP m dot p into G. Actually, if you see, ISP I had given, that's the reason I had given one box, full box, and there I told like it is V equivalent by G, or you can write m dot p into V equivalent, I mean just multiply and divide, so m dot p into G. So this m dot p V equivalent is nothing but thrust F divided by m dot p G. So here ISP they have given, so I will use this ISP, so I will get thrust. What is the thrust we have now? Thrust formula we have ISP into m dot p into G. G they have not given, so you consider 9.8. ISP you check what is the value of ISP. It is 280 second. No? 280 second. 280 second. This is what 280 second, and m dot p you have calculated, it is 24 kg per second into G is 9.8. So you need to calculate this. So thrust value you will get here. So this value you will have 65856, and this is nothing but the basically thrust. Okay, so obviously thrust, it is the force, so you will write in Newton because you have multiplied by 9.8. so now this is what thrust. What is thrust to weight ratio? So weight, how you will get the weight? How you will get the weight of rocket system? What is the weight of rocket system? So it is W, and weight of rocket system is the mass, initial mass basically. Okay, initial mass m naught. What is the initial mass? If you check, initial mass they had given 300 kg into 9.8. so if you get thrust to weight ratio, so actually it was cancel out. See, this is nothing but, I must say, ISP. Again I will write this ISP m dot p into G, okay, divided by weight is nothing but m naught into G. So this G cancel out, so what we will have? ISP m dot p divided by m naught. So thrust to weight ratio, it is ISP, I think it is 280. So 280 m dot p is 24 kg per second divided by initial mass is 300. If you calculate this value, so so total impulse, if you check, it is nothing but ISP MP into G, and weight is nothing but total weight, which is m naught into G. Okay, so in notes, I think previous class, previous class I had explained in impulse to weight. So there in numerator I forget to multiply by G, but in actually G will be there, so please correct that. Okay, so G cancel out. Now here it is ISP MP divided by m naught. So what is this total impulse? It is ISP, what is ISP? 280 into mass of the propellant, not mass flow rate, mass of the propellant. So what is the mass of propellant? I think it is 120. It is 120. Mass of propellant is 120. divided by total initial mass, which is nothing but 300. Okay, so if you do this, so it's a 280 into 120 divided by 300. So it is 112. Okay, so total impulse by weight is what? This. So all the data what we have calculated, this is 6, this is 5, and okay, fifth point, no? Fifth point, and this is what? Fourth one is here, 3 is here, check, match all the answer, and 2 is here. Then this is the first. Done. Fine. So this problem hope you all understood. Now we'll go for next problem, and it's very formula based problem. Okay, all rocket propulsion problems are formula based only. So now this is problem number 3. So now a single stage chemical rocket with ISP, specific impulse, 250 second is designed to escape with the following mass. Here they have given ml. What is the ml? Payload mass. How much? It is 200 kg. ms structural mass. How much? 800 kg. Total mass, or you can say initial mass. Total mass, it is given 30,000 kg. Determine number 1. We need to calculate mass ratio. Mass ratio means MR. Second one, velocity increment. It is delta V. Payload fraction. Payload fraction, what I remember, I think it was denoted by this symbol, lambda. Fourth is structural fraction. I think it was denoted by delta. Okay, and it is clearly mentioned assumed. They said no drag, no drag, no drag loss, and no gravity loss. Okay, done. I hope this one is very clear to everybody. Now we'll go and calculate this. It's very nice, very simple problem. So number one, they are asking mass ratio. What is MR? MR is nothing but MF divided by M naught, or sometimes it is called MB, burnout mass, M naught. What is the final mass? Final mass, if you remember, it is M naught minus MP divided by M naught. Check propellant mass, they have not given for this problem. So again, one more thing, you know, if I will write initial mass M naught, start from payload ML plus propellant plus structure. If you remember, this was the formula. For that reason only, in my previous lectures, always used to write formulas many times. The same formula I had written many times. Why? Because it should hit in your mind, and at the same time also I also can remember. If I am writing again and again the same formula, then definitely I will remember. So this is also the reason why I am writing every time the formulas. M naught minus MP. What is M naught minus MP? It is nothing but ML plus MS. If you check ML, I think given it is 200 and MS is 800. So it is 200 given and it is 800 it is given. How much? 1000, right? Fine. So what is the mass ratio? It is M naught minus MP divided by M naught, and this is also M naught minus MP is also ML plus MS divided by M naught, and it is 1000 divided by, what is the initial mass? I think it is given M naught 30,000. If you solve this, I think you will get, let me correct, find 1000 divided by 30,000. It is 0.0333. So MR 0.033. Okay, this is the first answer you got. This is the first answer you got. Now we'll go for the second one, velocity increment. How to get this? Second, they are asking what is the velocity increment. Or it is also called change in velocity. Okay, so it was delta V. Here clearly they have mentioned no drag loss, no gravity loss. So we have the formula, and what is the formula? Simple one, 1 upon MR. Check ISP, I think they have given to us. ISP here it is given. So the same formula I have given in terms of ISP. So what is in terms of ISP? V effective exhaust velocity will be ISP into G ln 1 by MR. So now this delta V, if you write ISP, obviously we'll write the value directly because no need to write the formula again. ISP they have given 250. If G they have not given, take 9.8 ln in bracket 1 upon MR. Just now MR you have calculated. So this value delta V, which is also called increment velocity or change in velocity in rocket, 833.93 meter per second. 8,332.93. Very nice. So this is the second one, right? And believe me, this type of question they are asking in exam. You solve previous question, you may get simple formula based problem they will ask to you. Now we'll go for payload fraction. Point 3 is payload fraction. So what is the payload fraction? If I am not wrong, it is lambda. So lambda is nothing but, what I remember, it was ml by m naught, because it is payload fraction. So payload mass, which is ml, and initial mass m naught, ml by m naught. So ml, here it is given, payload mass is given 200, and in m naught is nothing but 30. So 200 divided by 30,000. How much you will get? 200 divided by 30,000. It is 0.0066. This is the value of payload fraction. Now we'll go for the next, which is nothing but 0.4, and I think it is the structural fraction, right? Structural fraction. Okay, right. So find structural fraction, and it was denoted by delta. What is delta? It is structural fraction. So mass of the structure divided by initial mass. Mass of the structure separate they have given to us. So 800 here divided by how much? Check. 800 divided by 30,000. 0.0266. So this is the structural fraction. This is the payload fraction, change in velocity, and this is the mass ratio. So if you check previous year gate problems, okay, rocket propulsion problem, so they are asking similar kind of question. Means these are the data and they will say calculate mass ratio, mass fraction, or change in velocity, or sometimes called incremental velocity, or ISP. Means direct formula based. If you know the formula, very easy way you can solve. Okay, hardly in examination, hardly it will take 3 to 4 minutes here, because we are writing each and every steps, and in examination directly, you know, few things you have to write and few things directly you can keep in put in calculator, virtual calculator, and will get that value. So I would suggest for the rocket propulsion problem, because it is very easy and formula based problem, it is not complicated and very short whatever value if you put properly, you will get correct answer only. So I would suggest, once you are solving rocket propulsion problem, so keep calm, okay, because numerical will be very easy, formula based only, calculation you need to take care, because if you know and in very hurry, if you put wrong values, so definitely you will get wrong answer. So for that rocket propulsion problem, I will suggest it is for 2 marks. So please keep calm, go slow and calculate properly, and then find answer. And if it is fill in the blank, then fill that data. Otherwise, if it is objective MCQ, so obviously it will be very easy for you. Okay, it's very simple problem only they are asking in examination. So this was the problem. All right.